Welcome to this video presentation by the postgraduate student whose poster it represents. We will miss the bustling crowds around the posters at the All Energy Conference this year, but we hope you enjoyed this online version that we have created. Before the presentation starts, I would like to acknowledge the support of our generous sponsors. Without this support, the competition could not proceed and the winning entrants would not receive a financial award. Our platinum sponsor is the Victorian Government through the Department of Environment, Land, Water and Planning. Its brands include Victorian Energy Compare, Victorian Energy Saver, Victorian Energy Upgrade Program, Energy Scorecard and Energy for Business. Their contact details are on the slide. Monash University's Monash Energy Institute is one of our silver sponsors. With over 170 staff involved, the Institute has a vision to bring people together to solve global energy problems. The Monash student posters in this competition represent some of that work. Baywa Renewable Energy is another silver sponsor. Baywa develops both wind and solar projects in Australia as part of a global energy portfolio. Baywa staff have also supported our AIE events in the past, including our Young Energy Professionals Speed Networking events. Our final silver sponsor is the University of Melbourne's Melbourne Energy Institute. Many of you will have attended their regular forums that keep the energy community and public up to date on technical and policy energy matters, and the University of Melbourne posters in this competition reflect some of that work. Seed Advisory is our bronze sponsor, and this small but well-recognised energy consultancy covers both the technical and regulatory fields. Seed Advisory has been a regular supporter of the AIE and a presenter at our events. Lastly, we thank All Energy for hosting our live poster events over the last decade, and we look forward to doing this again post-COVID. These last slides show you our poster winners in the last competition. And I now hand you over to the poster presentation. Thank you.
Welcome to my presentation that will discuss my research project, Engineering Bacteria for the Electrosynthesis of Sustainable Fuels and Chemicals. Before I begin, I would like to acknowledge my PhD supervisor, Associate Professor Victoria Haritos, for her guidance on this project, as well as the Department of Chemical Engineering at Monash University for their assistance and providing the resources necessary to complete the project. This research is also supported by an Australian Government Research Training Program scholarship. As is now common knowledge, increasing greenhouse gas emissions is a predominant challenge that needs to be overcome by modern society. As our reliance on fossil fuels for transportation contributes to this issue, considerable effort has been directed towards implementing electric vehicles to replace the conventional combustion engine. However, despite this effort, in order to maintain our current global trade infrastructure, liquid fuels will still be necessary for the high energy applications such as shipping and aviation. As a result, alternative liquid fuels need to be developed for these purposes. Isobutanol is a prospective compound that can be used as an alternative fuel. It has similar properties to gasoline, making it compatible with the existing fuel structure used in the previously mentioned high-energy applications. However, disadvantageously, the conventional methods for its production still rely on fossil fuel sources such as propylene. So production through this manner would make the isobutanol produced as an alternative fossil fuel redundant. As a result, a sustainable method of production needs to be developed. Use of E. coli can work to resolve this issue and allow for production of isobutanol to be sustainable. It is an industrially applicable bacteria with a fast growth rate, so it can be cultured quickly and in a short amount of time. It is robust, making it very user-friendly, and it can be easily engineered to produce a wide variety of carbon compounds. For instance, only 2 non-native enzymes need to be expressed into E. coli for the cells to start producing isobutanol, as well as another valuable chemical, 3-methyl-1-butanol, through a modified amino acid production pathway. Although this does allow for the sustainable production of the butanols to occur, the process still relies on a food-grade product, glucose. This is not the most beneficial scenario with the growing global poverty, but this can be also further improved. Microbial electrosynthesis is an emerging technology that works to improve conventional biological production methods. This technology functions in a similar way to conventional electrochemical systems, but instead of relying on a solid material, a microorganism instead used as the primary catalyst. In this role, electricity is applied to the microorganisms to provide the energy necessary for metabolic productions. In doing so, this mitigates the reliance on using an electron-rich carbon source, like glucose, to produce the energy-rich products, such as isobutanol. Instead, electron-deficient compounds, such as the greenhouse gas carbon dioxide, can be converted by these microorganisms into alternative fuels using only renewable electricity to power the process. To meet this goal, we have so far expressed the enzymes KIVD, which is a ketoacetycarboxylase, and ADHA, which is an alcohol dehydrogenase, into a strain of E. coli. Through culturing this strain, we achieved both isobutanol and 3-methyl-1-butanol production. Most of the production of the butanols could be achieved within the first 24 hours, but this could be further increased with the addition of sugar at the 24-hour mark. To further develop E. coli for microbial electrosynthesis, it must also be engineered to be able to accept an external source of electrons. This can be done through engineering the conductive proteins from other bacteria into the cells. These proteins allow for the cells to transfer external electrons inwards through direct contact with the cathode material. Through engineering these ion-based proteins into E. coli, not only does this make them conductive, but it also results in a red coloration of the cell. When engineering multiple things into bacteria, this can have undesired effects on the performance. However, through developing a strain that contains the capabilities of both isobutanol production and an external electron transfer mechanism, no significant effect was observed on the production of the different butanols. Currently, we have developed a strain of E. coli that is capable of producing isobutanol and accepting an external source of electrons. This will be further developed through now applying these cells in a microbial electrosynthesis apparatus to investigate how the application of electricity improves the production from glucose. The system will be further developed so that E. coli can utilize carbon dioxide instead of glucose to produce the 2 butanol products. The potential of this project demonstrates that a simple microorganism like E. coli has the potential to make a huge impact in how we produce viable energy for the future.